Hey, so our next speaker is Jamie Whiteford, and Stuart is not going to go away. And so we're going to have both these speakers available after Jamie speaks to answer more of these questions and to raise more questions for you to ask. So thanks, Stu. And Jamie, are you ready to rock and roll, to irrigate us?
Rock and roll. Okay. Let me see. I think I need to get to share screen.
So Jamie is in with the Resource Conservation District in Ventura County, and he covers into the Santa Barbara Resource Conservation District, the Kachuma Resource Conservation District, and he's been a grant writer, and he's been a biology teacher for many different Ventura and Santa Monica and Riverside County or community colleges, and he knows people and he knows plants and he knows irrigation and how they can go wrong, and he's going to help us understand that. So take it away, Jamie.
All right, I'm going to try to do that by getting to the start of my talk. So, oh boy, Stu, wow, you'd think that we collaborated on this talk here. So awesome job. I appreciate that. You teed up a lot of things that I'm going to discuss. So hello, everyone. As Ben indicated, my name is Jamie Whiteford. I work for the Ventura County Resource Conservation District. And I started about 12 years ago here at the district. And I started out doing irrigation evaluations for the district. And I've sort of moved into doing other things as well. But irrigation efficiency is near and dear to my heart. So thanks, Ben, and thanks, Avocado Cafe, for asking me to talk. So what I'm going to discuss today is distribution uniformity. Stu touched on it briefly earlier and the importance of it. So thank you, Stu, for that. You know, and what I'm going to talk about is sort of distribution uniformity field observations. So really what I'd like to do is kind of walk through the stuff that we see when we're out doing irrigation evaluations for growers. And so with that, I'll get into a little bit of nomenclature just so you kind of get an idea of what I'm referencing when I'm talking about irrigation system stuff. So looking at the slide, starting at the top, you're going to probably hear me talk about the Mobile Irrigation Lab, or MIL. So the Mobile Irrigation Lab is a program that we have here at the district, and the role of MIL is to provide irrigation evaluations for growers. And in addition to the evaluation itself, where we come up with a DU value, you know, that 0.9 or 0.92 that Stu was talking about earlier, we're also out there to observe and offer recommendations for ways that, you know, growers can address any inefficiencies in the irrigation system. So when we get out there to the field, there are things that we're going to be looking at. And so looking at sort of this irrigation system in front of you, you know, there are mains that bring in water, usually larger diameter pipes. Then they get diverted into sub-mains, and then those sub-mains get to risers. And usually, you know, the sub-mains and the mains and the risers are at least somewhat buried, so you don't really see them much. But here in this case, you can see that they're elevated above ground. So the risers then connect to the laterals. So these laterals are the polytubes, you usually call them. And that stuff you usually see. And then, of course, the laterals are conveying water from the mains and sub-mains and through the risers into these laterals. And ultimately, that water is getting emitted at your trees through the emitter. And then if we look at that insert in the top center of the slide, you'll see here is just an example of a typical fan jet emitter. Going back to what Stu had said earlier, you know, pressure compensation is a big deal. It's much more standard now than it was before. And there's different ways of introducing pressure compensation into systems. In this case, the fan jets have this insert that's put right below it to regulate that pressure and hence the flow. And then the insert on the right, just another sort of example of the stuff we commonly see, where we have this riser and it attaches to a unit that's a pressure regulator. So this is a pressure regulator at the riser. And then that feeds into that T and into the lateral for distribution of the water. So these are just the typical nomenclature and stuff that I'm going to be talking about as we move through this presentation. So I'll talk about risers, and I'll talk about riser regulators, and I'll talk about PC emitters and all that stuff. So with that, we'll move into the first consequential slide, if you will. So irrigation system management, distribution uniformity. So what do we mean by distribution uniformity, or DU? Well, to me, it just really means that DU is a measure of how uniformly the irrigation system disperses water. And I just want to make the distinction that there's a difference between good DU, there's a difference between good distribution uniformity and efficient water use. Okay, because water use, it depends on kind of what you're trying to achieve. But distribution uniformity is about the uniform application of that water at the field level. Now, why do we care about DU? Well, we care about DU because we want to apply our water, and in the case where fertigation is happening, which is very common, we also want to apply that fertilizer uniformly to the entire crop. And ultimately, at the end of the day, good distribution uniformity, good DU saves water, saves energy, reduces water pollution. You get healthier trees, you reduce your inputs, and ultimately it increases profits because you're getting good yields, you're reducing your pest costs, and you're reducing your input costs. So you'll see that picture on the bottom left, DU. Do these emit the same amount of water? I mean, ultimately, that's what we're trying to do, is we're trying to see in your irrigation system, randomly sampled throughout the irrigation block, do all the emitters within that block, or at least a subpopulation of those emitters within that block, emit a uniform or the same amount of water? If yes, then that's good. You've got good DU. And Stu showed a picture similar to the ones I'm showing here, where you got good DU, you've got good uniform application of water, it's hydrating your roots across the entire block, and so you're getting good production. You're also getting even distribution of that fertilizer, et cetera. But if your DU is if you're not getting the same amount of water emitted from your emitters, then that's bad. And so there's a picture of bad DU. You've got overhydrated trees, you've got underhydrated trees, and you got dead trees. So we want to avoid the bad DUs if we can. Now, I want to just circle back to efficient water use. You could have good DU, like that top picture, where just the bottom of your root zone is being hydrated, or you can have good DU and bad water use efficiency, where you're just wetting that entire soil profile well below the root zone. Now, if you're managing salts, that's fine. But if you're doing that all the time, then frankly, you're wasting water and you're wasting fertilizer. So that's a topic for a different talk. Distribution uniformity, standard method. So Stu talked about low quarter distribution uniformity, DU-LQ or LQ-DU. That's a standard practice. And this is a point I think is important. It's wonderful to have a standard practice, because what that means is that we're all talking the same lingo. When I say, I was out there and I measured a DU of 0.71, and I say that to a farmer, that means that I took the same approach as everybody else takes for measuring that value. And so we're talking apples to apples. So he knows that I went over to Farmer A and I got a DU of 0.88, which is great. But then I came over to his farm and I did the same exact standard practice, and I came up with 0.71. So all things being equal, he's under par for farmers in his area. All right, so how do we get to that value? Distribution uniformity, or DU. Calculating DU requires measuring and comparing flows. And again, we use the low quarter DU method that was adapted from ITRC's procedures. And as you've probably already heard many times before, we need to have DUs that are upwards of 0.85, especially for micro sprinkler irrigation systems to, say that that's a good system DU, and for drip, you really want it above 0.9. And it's notable that these DUs aren't at 1, and the reason is because, as Stu pointed out, no system is perfect, and so you're never going to get 100% DU. Well, you might, but there are inefficiencies in a typical system, and so again, 0.9-ish is acceptable. Now, how do we actually measure it? The way we measure it is we have to first get gallons. We got to figure out what your flow is. So we measure gallons from the emitter, and we do that over a set period of time. So that gives us gallons per hour. So there's your flow. And the way the low quarter DU system is set up, when we go into an irrigation system, what we do is we sort of evaluate it first, figure out how we're going to do that sampling. We go in and we get any number of samples, 24, 36, 40 samples out of that irrigation block. And we look at what those pressures say, we look at what the flows say. And what we do is we take that whole subpopulation of samples and we break them up into quarters. And we take the average of that, the lowest quarter or lowest 25% of the total population, and we divide that by the average of the system. And you can see that calculation in gray there towards the right side of the screen. So we take the low population, we divide that by the average of the population, we come out with a number. And all of us do this. All of us follow the same protocol. So whether Stu's doing a DU or I'm doing a DU, we're going to come up with, we're going to use the same approach to come up with a number. And that's how it's apples to apples comparison. And again, I want to point out, measuring your DU doesn't necessarily solve your problems. It just helps identify what the problem may be. Okay, so our job is to point you in the right direction. Your job is to fix it. All right, distribution uniformity. What affects DU? All kinds of things that affect DU. Pressure, friction, and system integrity all play a role in affecting DU because, as Stu indicated, the system was designed so that all of these factors balance to deliver the expected performance. However, just over time, wear and tear, that balance can shift. So the factors that that affect DU and that we're interested in addressing include water pressure, because water pressure is what makes water flow, and that pressure can be either too high or too low, or just right. Friction loss is also another factor. It reduces pressure. Perhaps it reduces the pressure too low to support flow. And again, this goes back to what Stu was saying. There's nominal flows, and then there's necessary flows in order for some system components, particularly emitters, to work properly. So you got to have the right system pressure in order to be able to get what you expect out of your system. And then, of course, system integrity, or the ability of that system to deliver uniforms at desired outlets, and hopefully that would be emitters. And so these are the factors that need to be addressed to maintain good DU. Basically, you want to make sure you have uniform flows at your desired outlets or emitters. And so pressure, that's provided by your pumps, elevation. So you really need to know what your source pressure is to help isolate issues. You got to know what you're starting with to know what you might end up with. Friction, those friction losses are due to turbulence in the system. So the more kinks, changes you introduce, the more you're going to affect that friction loss. So be careful with your system changes. You're adding on a whole nother set of trees. That's going to upset that balance of your system as it was originally designed. And then, of course, normal everyday wear and tear happens. So maintenance is key. Okay, you got to walk, you got to look, you got to listen, and you got to fix. Okay, the fix part is what's important for y'all. For us, when we're out doing DUs, we're going to walk, we're going to look, we're going to listen, and we're going to measure. So that's the difference. We can measure stuff. It's up to you to fix it. All right, so what I want to talk about here is I just want to go through, we're going to have 3 slides that look kind of like this. And what I want to talk about are those factors that I just introduced: water pressure, friction loss, and system integrity. And I just want to go through some of the stuff that when MIL staff are out in the field conducting an evaluation, the best we can do is troubleshoot to try and identify what issues may be present. The way that we troubleshoot is to walk, we look, we listen, and we measure. We walk the whole block to get a feel for how it's designed so we can determine how best to collect our DU sample population. I mean, we don't have time to measure every single emitter out there in the block. So what we do is we sort of break it up into logical subpopulations, and we take measurements at those emitters. We look and we listen for things like leaks and indications of high pressure. I mean, you can hear when an emitter is under high pressure. You know that, right? You can also see it because you see this aerosol mist where you just got all this water just shooting out those emitters at very fine droplet size. And what we measure is flow and pressure. So we actually, have a pressure gauge out there for pressure measurements. And like I showed in the slide earlier, we're actually capturing emissions over time for flow. So what I'm going to talk about, or what I'm going to point out, are some of the issues we commonly observe in the field that affect DU and what the potential solution might be. And there could be multiple solutions to the same issue. In this slide, I'm just going to be focusing on things that affect pressure. I'll discuss friction and system integrity in subsequent slides. So don't have a whole lot of time to go through all this, but want to start off in the first line there in this table. The issue is the pressure is unknown. Please, come on now. You have to know what you're working with. So you need to put in some pressure gauges so you understand what your source pressure is, and then see what your pressure is through that irrigation system. That way you can see if there are problems with it in terms of pressure losses. If you're out there and you do have pressure measurements ability, and you have low pressure at your well or your source, then that's going to be a problem because frankly, you're just not going to have enough water supply. So you need to either, if it's a well, repair your well so you get the flows that you need. Or if you've got a tank where you're holding the water, that tank may be undersized, you just don't have the head pressure that you need for your system to work well. Or you just have too much water, too little water coming in your system if you're on a municipal supply, for example. So maybe you need a larger meter just to get more water and better pressures for your system to operate properly. If you notice that you have low or very high pressure and your source is okay, then I mean this could be an issue where you have failed or undersized pipes, or consider a variable frequency drive. Your pump could be failing, or it could be undersized, so it's just not providing enough flow. Or in the case of if you've got a consideration of a variable frequency drive, maybe you just need to change the settings on that. One of the problems we have is that with a direct drive pump, you're just pumping too much water and you have smaller blocks, and so you get really high pressures. Well, if you have a variable frequency drive, you could always back that off by changing the settings, or it would do it automatically. If you got low pressure you're seeing in your system, and you got a fixed supply, then the issue might be that you've simply got you need to reduce your block size. You might have too much simultaneous demand. So you could reduce your block size, or you could reduce the number of emitters to get things to operate again efficiently at that emission level. If you've got low pressure that you're noticing in the system and your source is okay, then it could be you have too small diameter pipes, or your pipes are just too long, and that's leading to much friction loss, which is reducing your pressure. So you could increase your line diameters, or you could decrease the lengths. I see sometimes people just adding on pipe to add on more trees to an existing pipe, and it's just really dragging down the overall emissions for that system. If you got high pressure in your submains, that's just going to lead to more leaks. It's going to overstress the system. So, install reducing valves or use regulators on risers to maintain that pressure. So you're not over irrigating in places you don't need it or want it. And I want to point out that we have different ways of regulating pressure. You can use regulators on risers. So that's that third picture down below. That will regulate or address elevation changes up and down slope. So if your submains are going up and down slope and you got your risers coming up, and then you got your laterals teeing off of that, if you want to address that up down slope pressure, then regulators are a way to do it. And then if you look over to the right, that bottom picture, this shows that diaphragm that Stu was mentioning earlier in a PC micro sprinkler. You can, if you have high pressures in your laterals, this is the way to go. You can add in PC emitters. And the real role of PC emitters seen is just to address elevation changes along the contours. So, not all contours are going to be perfect in elevation. There's going to be some that run a little bit upslope, a little bit downslope. These help address that. And I also want to point out that second picture down the bottom, a lot of poly just looks identical from the outside, but we've run into a situation where they look identical on the outside, they're not identical on the inside, and that differences in inner diameter are important because inner diameters that are smaller, or pipes overall that are smaller in diameter, are just going to have a higher friction loss. And so if you're substituting pipe and they're not the same, then you're going to introduce higher turbulence in those smaller diameter pipes, and you're going to introduce friction losses, and that's going to affect your flow. All right, so this was just a kind of bunch of stuff that we kind of see when we're out there, helps us pinpoint where there might be issues, and helps us then provide some kind of recommendations. And this is just talking about water pressure. If we want to talk about friction losses, again, friction losses is just one of those things that leads to poor distribution uniformity. And the reason that friction losses leads to poor distribution uniformity is because it reduces the pressure and flow. It results from turbulence as water moves through the system. There's really not a whole lot you can do about that other than having pipes that are a little bit smoother so that you don't get as much turbulence. And it's important. There's actually differences in the pipes and their ability to reduce or mitigate against friction losses. If you look at the two bottom pictures, you'll see there's 1/2 inch all the way to 1 inch pipe. And the one on the left is PVC, and the one on the right is poly. So the PVC pipe is usually what the submains, mains, et cetera, are made out of, and the PE is that poly tube that's black and laying on top of the ground. But you'll see that for the same flow, the same GPM, you're going to have PC losses that vary. So if you look at the 1/2 inch for the PVC at 1 gallon per minute, you got a PSI loss or a friction loss of 0.22. If you look at 1/2 inch for polyethylene, you're going to see at 1 GPM 0.49 PSI loss. Okay, so there's differences in piping. If you want to substitute, a 1 inch PE for a 1 inch PVC, you're going to introduce differences in your losses for friction. So just be careful with substituting stuff. It does make a difference. Lower pressure, I just want to talk about some of these issues we see. If you see low riser pressure, but your source is okay, your source pressure is okay, you probably do have an undersized main, submain, or both. And again, that's because friction losses is higher in narrow pipes and wide pipes. And that's again going to reduce your velocity. It's going to affect your flow. So again, be careful with substituting different pipe sizes or different pipe types. If you got low riser pressure, your source pressure is fine. You probably got a line break somewhere, assuming everything is sized correctly. So please find that line break, walk and look for soft ground. Listen for water flowing that you can't see. Low lateral pressure, your riser pressure is okay. If you got low lateral pressure, you probably got undersized lateral. So maybe you need to go from a 1/2 inch lateral to a 3/4 inch lateral. Again, because the increase in size reduces friction losses and you get better flows. Or perhaps your laterals are too long. Maybe you just kept adding on trees and adding on laterals to the same riser and you just got beyond thresholds. If you're low if your pressure in your laterals are low, your risers are okay, then maybe you got too many connections on that lateral. And again, that might be related to just having a longer lateral as you added on emitters for trees that you put in. If we look down at the pictures on the bottom, you can see, undersized laterals, a lateral's too long. Like that's my colleague Vic there in that third picture over to the right, and he's standing there at the top of a slope. So here we've got a small submain, and it's upslope. So his water source got to pump it up there or get it up there. It's already at low pressure, and then it's hitting undersized pipe, so it's going to have friction loss. And the only good thing is it's going downhill from there, so it'll pick up some elevation PSI. But other than that, maybe some consideration for how to redo that block. And then I also want to point out the picture on the right bottom. I see this a lot there, where people are just making all these connections from one lateral to the other lateral and adding on laterals, and just it's a crisscross of an applesauce kind of situation, and it's just a lot of friction losses in those small poly pipes because of the friction losses, and also all the connections, and also just the roughness factor for that pipe. And then I want to talk about system integrity. Again, all of these are sort of observations that we see. Again, we're walking, we're looking, we're listening, and we're measuring. And so these are kind of stuff that are a combination of just system integrity breakdowns that we notice. Keeping in mind the irrigation system maintenance is what sustains uniform flows to the desired emission point. So, going back to Stu's talk earlier, when these systems were designed, everything was balanced. You knew what the source pressure was, you knew what the runs were, what your uniformity goals were. But over time, things just sort of get changed. And so they may have been uniform back then, but changes could lead to issues now, particularly with maintenance. So oftentimes we'll see low riser pressures, but the sources are all right. That could be just a line break, or something's restricting flow. Got laterals down on both sides of the riser. This is a common problem where riser screens are still in place, and those are just catching all the debris in the water. Or there's an inflow filter on the line, and so all those things are plugged, and nobody's out there getting rid of that stuff, and that's plugging up the whole lateral. If you got a single emitter, just know where it's low flow, it's probably blocked, so unplug it, or check your spaghetti tubing. Could be something stuck in that as well, if it could make it through the plug. If you're going to replace your emitters because they're plugged, please use the same type. Or at least the ones that are going to give you the same flow under your conditions. If you've got a PC emitter that's out there, and it's a PC emitter, and it's too high, as Stu indicated earlier, check the diaphragm, because they sometimes are removed by field crew, believe it or not. They don't work if they don't have the diaphragm. If your emitter flow is too high, then just replace it with a PC type and don't toss away the diaphragm. Okay, or regulate the laterals at the emitter. At the riser. And keep in mind, again, PC types are needed if the lateral elevation varies. So if you got laterals running upslope and downslope, then you're just going to get more water downslope than you will upslope if you don't put some kind of regulation in. And in this case, PC types are preferred for that. If you've got low flow from emitters at the end of your laterals, then you probably got debris at the end of your lateral. So what happens is all that amendments and stuff that you add to your system, or anything that gets sucked into your system, it all ends up at the end of the laterals, which plugs up the emitters down there. So open up your lateral ends, clear that debris out. If you see or hear breaks or leaks, fix them. They're outlets. They're not emitters. Okay, it's great that you're getting free emission, but those are going to be at pressures and flows that aren't going to fit with the rest of your system. If it's aged, replace it. If it's wildlife, give them water so they'll stop biting through your system, or at least slow it down. If you've got low or high flow across your entire lateral, check your regulator for plugging and failure. Again, these are components that do wear out. debris can get trapped in there, the spring wears out, whatever. So make sure to check those and replace them if needed. And if you got low flow, your entire lateral, check the riser screen or check the lateral filter for plugging and clean them out. And the other important point is figure out where that debris is coming from. You may have a break somewhere in the line, and when you're shutting down your system, that back pressure comes and it just sucks all that stuff in, and then it distributes it throughout your irrigation system. So that's going to lead to huge problems down the line. So find out where you're getting your debris from, or if it's the case that the filter is not doing its job, then you need to replace that filter with one that works better. All right, and so now I'm just going to get into a slideshow of stuff we see, just to prove the points that we made earlier. Okay, that first set. Notice anything missing? Believe it or not, people do take out the diaphragms from PC emitters and toss them over the shoulder, just like Stu said. They don't work without the diaphragm. Here's a picture, second set, just showing clogged filters. So there's a filter on the left that I see commonly. There's a filter in the middle, inline filter, right past the regulator. And then there's the debris that's caught up. The big question is, where's that stuff coming from? You got to get that stuff out of the system. You got to fix that leak. You got to figure out where it's coming from and address that, because there shouldn't be that kind of material in your lines. Going back to what Stu had mentioned earlier about burying drip. Okay, so you see that picture on the left side. Those are all drip emitters. You got clean water in 3 out of the 4. That fourth one, that's got organic matter that's been sucked in because it's been buried underneath that mulch. So just be careful. That means that material is getting into that emitter. And yeah, if it's clogged, you still have 3 that works, but wouldn't you rather have 4? So be careful with that. All kinds of stuff can get into your emitters. There's some organic debris caught up in a typical micro sprayer. So be careful. Back pressure can suck in material. Insects love to get into emitters because there's water there, and then they get stuck. And even weed whacked, believe it or not. I've seen weed whacked material somehow miraculously get stuck into the orifices for these emitters, like fan jets. So always keep a safety pin handy, just in case you need to clean out an emitter. There's a riser with no pressure regulation. Hopefully there are some PC emitters on the lines to regulate that pressure. Here in Ventura, we've just got so much slope that, it's always good to have some kind of pressure regulation. Plug screen, riser screen, you see that in the middle there. Used to be recommended to keep those things in, but then filtration can stand a practice. So I'd recommend taking them out, because if you don't and they get clogged, down goes your entire lateral, both sides. And again, be careful, figure out where that stuff is coming from. And then the bottom there, okay, this is from the same irrigation block, 4 different types of fan jets. Now, I want to caution you that if you're doing this for a management perspective, like you need different flows because you got mature trees versus you've got younger trees, then I suppose that's understandable. But if you're going to do that, they need to be operating under the same kind of flow conditions to get the performance that you need for those different things. But if you're just allowing your irrigator to go in and just swap out whatever emitter happens to be in its fanny pack at the moment, then you're missing you're setting yourself up for poor DU and ultimately inefficient use of your water and your fertilizer and all that stuff. So maintain uniform emitters if you want to at least try to get uniform emission. High pressure, going back to that rainbow effect talked about earlier, you can usually tell when you've got high flows just because you've gotten all this mist and you catch rainbows from that aerosoled water. Good indication that you need pressure regulation. That middle picture, leaks are leaks. They're not emitters. They may be right next to where you want to emit, but they're leaks. So there's no pressure regulation, there's no flow regulation. So please fix them, and they're just going to turn into bigger leaks. So that's not going to help you. Chemical plugging, on the left, we see a drip emitter clogged up. Stu had mentioned it earlier. Run some acid through that to clear it up. Do that regularly to keep them clean. Chemical precipitation is a tough one. You got to stay on top of it. You got to figure out how to address it early on. And there's some manganese there for your pleasure on the right. So, use acid, use filter, and use the right filter. All right, so I probably went way over my time. I forgot to set my timer. But anyway, that's the end of what I want to talk about and show you. And the end. Questions?